This video is about differentiability, and this is in the context of calculus where we've already discussed limits, we've already discussed the definition of a derivative, and so now we're going to use those things. Our notes will begin with a definition where we'll say a function f is differentiable at a if f prime of a exists. Now we've already seen some notation for derivatives, and f prime of a is one such notation or way to represent a derivative. Of course, it would mean the derivative of f at a. It is differentiable on an open interval a to b, or a to infinity, or negative infinity to a, or negative infinity to positive infinity, if it is differentiable at every number or every point in the interval. To help understand this definition better, I think this example works really well. We want to consider the differentiability of the function f of x equals the absolute value of x at x equals 0. Now, you'll recall that x equals 0 is a really significant place for this function in particular. Now, if you remember that we've already used this function, you can define it as a piecewise function where the absolute value of x is equal to either just x or negative x, depending on where you are. So the absolute value of x is equal to x when x is greater than or equal to 0, but it's equal to negative x when x is less than 0. And so we're going to kind of borrow that distinction or two areas to look at for this particular example of investigating the differentiability of this function. And then we'll tie it all together with some review of what the graph of this function looks like as well. Since we're focusing on this function at x equals 0, let's consider what's going on surrounding that value so that we know how to analyze this function. For instance, if x is greater than 0, positive, of course that's on one side of 0, in that case, according to the piecewise definition of this function, we would say that the absolute value of x equals x. And similarly, for some small but positive h value, we could say the absolute value of x plus h would be equal to, well, x plus h, relatedly. And this, of course, is for some value of h greater than 0 but small. Now, we could say, using the definition of a derivative of f of x, so we'll call it f prime of x, using the limit definition we've discussed, would be written as the limit as h approaches 0 of f of x plus h, so that'd be the absolute value of x plus h, minus f of x, that's the absolute value of x, all over h. Let's take this limit a little bit further, right? We're certainly working in the case right now where x is positive. As we've already stated, that brings some facts with it that we'll be using here. We can say, or rewrite this as the limit as h approaches 0 of, now again, if the absolute value of x plus h is really just x plus h in this case, then we're going to write it that way. We'll say this is really x plus h for the first absolute value in the numerator here. Secondly, minus absolute value of x. Well, again, we've called that x already above. And so we'll have x plus h minus x in the numerator all over h. If we simplify this a step further, we have the limit as h approaches 0 of, well, x plus h minus x is just h over h, but h over h is really 1, and so this limit turns into just positive 1. Now that's the case when x is positive or greater than 0. Let's consider next, though, that if we're surrounding x being 0, what if x was less than 0? That certainly could happen, surrounding 0. And so in that case, let's also go through some of these definitions. According to the piecewise definition of absolute value of x, then when x is negative, or less than 0 in this case, the absolute value of it would be negative x. And similarly, the absolute value of x plus h would be negative x plus h. There's a little dependence in this last expression here about what the value of h is compared to x. So the point is here, remember, h is just some positive value, but it could be as small as we need it to be. And we could pick one small enough to maintain this fact about the absolute value of x plus h being negative x plus h. So if h is small enough, it won't change the value of this expression, so this still works. If h were somehow too large, then x plus h could become positive even though we're considering that x is negative. So that's a possible problem here, but we know we can pick an h value small enough because all h has to be is something positive. It could be as small as we need it, which means we can cover the case where this will still end up with the same definition, negative x plus h. If we evaluate the derivative using the limit definition in this case, we'll say f prime of x. Remember, this is the limit as h approaches 0 of f of x plus h. Well, in this case, that would be negative x plus h minus f of x. That would be negative x all over h. This turns into the limit. If we reduce it a step or two, we have the limit as h approaches 0 of negative h over h, which is negative 1. If this limit exists, which it does, as we've now seen, then the derivative exists there. This is the limit definition of the derivative. What we've seen so far is that when x is greater than 0, the limit definition of the derivative, which we've now written out here, yielded 1 as the derivative, and that exists, which means that it is differentiable in that case. In the second case, when x is less than 0, we also evaluated the limit definition of a derivative and got a value of negative 1, which exists, which means, again, this is differentiable in that case. So what about when x equals 0, which would be the thin place between these two cases? So we've already done greater than 0, less than 0. What about when x equals 0? In this case, when we're centered on a fixed value, we'd want to compute f prime of 0. Does this derivative actually exist? That's our question. We're going to write this out using the limit definition like we've done in the previous two scenarios again. So we'll say f prime of 0 equals the limit as h approaches 0 of f of x plus h, but now x is 0, so we'll say absolute value of 0 plus h minus f of x, or in other words, absolute value of 0, x is 0 here, all over h. This reduces to the limit as h approaches 0 of the numerator is the absolute value of h, the denominator is just h. And so our question is, does this limit exist? Because if it does, then we would have to say that this function is differentiable in any such case. It's when x is positive, when x is negative, and when x equals 0. Those are the only three options. But if this limit does not exist, then we would say that the function is not differentiable at this x equals 0 place. So let's investigate this a little further, understanding our definition of limits and whether they exist or not. Let's explore by unpacking the limit as h approaches 0 from the left of this absolute value of h over h, and the limit as h approaches 0 from the right of the absolute value of h over h. As we've discussed already in defining limits, they exist when you have the limit from the left and the right agreeing. If we start on the left side here with the case where h is approaching 0 from the left, now if it's approaching 0 from the left, that means the h values are negative, but that would mean the absolute value of h is really negative h. And then negative h over h, the denominator is really negative 1. I'm running out of space there. So the first limit, as h approaches 0 from the left, of the absolute value of h over h, turns out to be negative 1. Now, from the right, if we consider the same thing, understanding the absolute value of h when h is approaching 0 from the right, those would be positive values. So the absolute value of h is just h there, which means we have h over h, which is 1. The problem we've now uncovered is that the limit of this derivative, this limit definition of the derivative at 0 from the left, which is negative 1, and the same definition of the derivative but approaching 0 from the right are two different values, which means by definitions of limit, this limit does not exist. You can go back to when we discussed the existence of limits and the definition of them. When a limit As h, or any variable, approaches something from two different sides, does not agree, the limit does not exist. What this means, though, in summary, is that the limit we were taking was the limit definition of the derivative of this function at 0. So we would say that this function is not differentiable, but only at this value 0. It worked fine when x was positive or x was negative, but when it's 0, it's not differentiable. The example we just looked at of f of x equals absolute value of x is a perfect example of the intricacies of this theorem. If you recall this function, if you remember the graph of this from maybe algebra class, this has a sharp V-shaped graph, which has a sharp point right at the origin. Now, in this case, we could say, if you go back to our definitions of, or definition of continuous, this function is continuous at 0, but we just discovered that it's not differentiable at 0. So think about what this theorem is saying. It's saying if f is differentiable, then it is continuous. But the opposite direction is not necessarily true, as we just saw. This function, absolute value of x, is continuous at a, but it's not differentiable when a is 0, that is. So we can see that there is a direction that matters to this theorem, and this is a good example to understand or explore it. Let's now consider graphical cases of non-differentiability. We'll consider 3 ways for f not to be differentiable at a. The first case is when you have a corner in the graph. This is exactly what happens in the absolute value of x function that we just saw an example of in detail. We discovered that that function, which if you recall the graph of it, has a sharp V shape right at the origin. We discussed that that function is not differentiable at 0, which is exactly where that corner or point or sharp point is. So anytime you have that in a graph, even if it's something else, not necessarily absolute value of x, then you would say it's not differentiable there. Secondly, a graph is not differentiable is indicated by a discontinuity. Now this is related to the theorem we just saw, which has a one-way implication, but if you negate an implication going the opposite way, like you could say in this case, if f is not continuous, like with a jump discontinuity or really any discontinuity, then it is not differentiable at that value. And thirdly, if there's a vertical tangent, we would say that the function is not differentiable there either.